Hi, this is John Whitaker for the probability class, and this is our 22nd video lecture. And I want to talk about more computing probability by doing conditional probabilities. And I want to start off with a definition. We're going to let E sub 1 be an event. Then the indicator function, or indicator random variable, very apt name, we're going to call it x sub e sub 1, is given by x sub e sub 1 is equal to 1 if e occurs, e sub 1 occurs, and 0 otherwise. So x just tells you, or x sub e sub 1 just tells you whether e occurred or not. As a fact, the expected value of x sub e sub 1 is equal to the probability of e sub 1. We're going to prove this in just a second, but we have seen this before, okay? And it was involved a little bit in the proof of Markov's inequality. So that's where you may have seen something similar to this, or where you did see something similar to this. Let's prove this fact. It's very short. So to prove, one thing to notice about x sub e sub 1, because it's defined to be just 1 or 0, what that means is that x sub e sub 1 is a discrete random variable. So the expected value of x sub e sub 1 is equal to the sum over x sub e sub 1 values of 0 to 1 of x sub e sub 1 times the probability mass function of x sub e sub 1 of x sub e sub 1. And so when x sub e sub 1 is 0, we're just going to be 0. So the only thing that's going to be any consequence here is 1 times f sub x sub e sub 1 of 1. But that's nothing more than the probability that x sub e sub 1 equals to 1. And the only time that x sub e sub 1 is equal to 1 is when e occurred. So that's the probability that e occurred. Okay? And so that ends the result. Another fact is that the expected value of x sub e sub 1 given y equal to y is equal to the probability of e sub 1 occurring given that y equals to y. And as a comment, this fact is true regardless of the type of random variable y is. But when y is continuous, the proof in that situation is beyond the scope of this class. So when y is continuous, the proof of this fact is beyond what we want to do in this class. So we're going to do the proof in the case that y is discrete. Then the expected value of x sub e sub 1 given y equals to y, okay, in the discrete case, that's equal to the sum over the x sub e sub 1 values, which are 0 to 1, of x sub e sub 1 times the probability that x sub e sub 1 equals to x sub little x sub e sub 1, given that y equals to y. That's its definition. This probability that I'm listing here is nothing more than the conditional probability mass function of x sub e sub 1 given y. Okay? That's what it's defined to be. Okay? Now look, when x sub e sub 1 is 0, we're just going to 0, so the only term of interest here is going to be when x sub e sub 1 is 1, so that's 1, and that just be the probability that x sub e sub 1 equals to 1, okay, given y equals to y, little y, okay, and x sub e sub 1 being equal to 1 is the same thing as the probability of e occurring given y equals to little y, and that's what we were trying to prove. And so that concludes the proof. Okay, we'd like to look at two more facts. Here's fact A. The probability of e sub 1 is equal to the sum over the y values of the probability of e sub 1 given y equal to y times the probability that y equals to y if y is a discrete random variable and part B, the probability that of e sub 1 is equal to the interval from minus infinity to infinity, the probability of e sub 1 given y equal to 1, okay, times f sub y of y dy, where f sub y of y is the probability density function of y. Okay, let's do the proofs of these. And so, to start off with, let us know that the probability of e sub 1 in general is equal to the expected value of x sub e sub 1. We've proven that in the previous fact just a few seconds ago. And that, by something we've done a little while ago, is the expected value of x sub e sub 1, conditional expected value, given y equals to y. And the expected value of x sub e sub 1 given y equals to y, that's equal to the probability, so this would be the expected value of the probability of E given y equal to y. And that was from the previous fact that we had listed. And I should call it E sub 1. Okay. Now for case A, we're considering y to be a discrete random variable. Let y be discrete random variable. I'm repeating some of the things that we just said. The probability of E sub 1, which is equal to the expected value of the probability of E sub 1 given y equal to y. Okay, so that's what we're taking the expected value of. And that's going to be equal to, so it's a sum over all y values, okay, of this random variable, okay, times the probability, so this would be the f sub y, the p mf of y, f sub y is equal to y. Okay. And that's exactly what we said it should be. So that ends part A. And for part B, if we let y be a continuous random variable, the probability of E sub 1 will be equal to the expected value of the probability of E sub 1 given y equal to y. And here in the discrete case, that's going to be equal to the integral from minus infinity to infinity. We're thinking of this as a random variable y. And so what this is going to be is the probability of E given, or E sub 1 given y equal to y times f sub y of y dy. And that's it. Okay, let's start looking at some examples. And that's what I want to do for the rest of the day, is look at some examples. Okay. Let's suppose, so here this is an abstract example. Suppose that x and y are independent continuous random variables having densities f sub x of x and f sub y of y. The question is for us to compute the probability that x is less than y. So here's a solution. This is from our text. The probability that x is less than y, we can condition that probability. So that's the probability, as we had just done, as we had just worked, we're talking about continuous random variables, so it's going to be the integral from minus infinity to infinity. The probability So we're thinking of this as E1, that x is less than y, given y equals to little y, times f sub y of y dy. And that's from the previous fact we have this result. All right. Here, what we can do, because we're given that y is equal to y, and we want big X to be less than the random variable y, that means that we want minus infinity to infinity the probability that big X is less than y, given y is equal to y, f sub y of y, and that relinquishes the dependence between x being less than big Y now at this stage. Okay? And so I can rewrite this, just needs dy, as an interval from minus infinity to infinity of the probability that x is less than this little y due to the independence, f sub y of little y dy. That's equal to, well, is equal to the interval from minus infinity to infinity of the probability that x is less than or equal to y, and the equal to part comes into effect because x is a continuous random variable. This, so equaling to y doesn't add anything. F sub y of little y dy. All right. Now, the probability that x is less than or equal to y can be represented, it is, by definition, the CDF of x evaluated y. And so that's how we can symbolize it. Now, this is just a symbolic representation of the answer where f sub x of y is really equal to the integral from minus infinity to y of f sub x comma y dx. I'm sorry, it's f of, I'm sorry, I made a mistake there. It's f sub x of x. Yeah, so this is CDF of x. So what's that? You find the probability that x is less than or equal to y. And that is, you integrate the PDF, the PDF of x. That's right. Okay, and that's our symbolic answer. Well, the next problem I want to do is wordy to get up. We'll start it here. And this is a more concrete example. It says an insurance company supposes that the number of accidents that each of its policyholders will have in a year is a Poisson distributed. Okay, I don't know if you remember Poisson or not, but that means that it's EMF, so I'll write this in parentheses, has the form, it's e to the minus lambda, lambda to the x, all over x factorial. And that's the form. So here, let me write down, I would be saying, that f of x, or x of x, or x, would be equal to that. That's what this distribution is. Don't forget the x is run from 0 to infinity, if you want to. Okay. With the mean, so the lambda we're talking about, of the Poisson depending on the policyholder. So for each policyholder, we're going to have a different lambda, if you will. And then it goes on to say that if the Poisson mean of the randomly chosen, of a randomly chosen policyholder has a gamma distribution okay, with density function we're going to call it G of lambda. This is a little bit confusing, so I'm following. This is a problem in our text, and I'm following its notation. But the lambda here is the input variable, and it's equal to lambda times e to the minus lambda, with lambda being greater than or equal to 0. That's what I have. So we need to review that gamma distribution. But before I go on, what's happening is okay. So we're talking about the number of accidents a particular person will have, and we're saying, well, it's Poisson distributed, okay, so it has this form. But not only are we saying that, but the lambda is going to be changing, okay? And so for an individual person. And the reason that this makes sense to me is that the way that we're driving at certain ages of our lives would make it more or less likely for us to have an accident. So when you're a teenager, maybe your reflexes are wonderful, but you're maybe not paying as much attention. And maybe when you're middle-aged, your reflexes maybe aren't as good, but you're paying more attention, so you're less likely to have an accident. Maybe then when you get a little bit older, you're not paying enough attention and your reflexes aren't so good. And so the lambda is changing depending maybe on your age. But we're saying it's gamma distributed for a particular individual. Okay, so I want to talk a little bit about this gamma to remind you what that was. At least what its df is. So recall, the distribution of a gamma random variable call it x with parameters alpha and lambda, lambda squared greater than 0, or lambda is strictly greater than 0, I should say, is, so here's what it was. It was f of x, it was equal to lambda, I think, times e to the minus lambda x, lambda x to the alpha minus 1, all over gamma of alpha. That's what it was. Okay? And so, what we had was g of lambda, we had lambda was gamma distributed. And that was equal to lambda times e to the minus lambda. The lambda over here is playing the role of x. Okay? And so what I'll say, if this is gamma distributed, that's what they told us in the problem. With parameters. So here, the alpha is equal to 2, and the lambda would be equal to, not that lambda, but the lambda that's represented over here. This lambda is playing the role of x. The lambda for it is equal to 1. The question is, after writing all that, what is the probability that a randomly chosen policyholder has exactly in accidents exactly in accidents next year. Okay, so this is from our book. Let's look at the solution. Okay, so we're going to let x equal the number of accidents that a randomly selected policyholder has next year. Let y be the Poisson mean number of accidents for this policyholder. Okay. Then, conditioning on y, we have, here's what our problem would be.
probability that x is equal to n. Okay, now y in this case is gamma distributed. Gamma is a continuous type of random variable, so this is going to be equal to the integral. And it's from 0 to infinity, because we're talking about integral in respect to lambda, and lambda is greater than or equal to 0. It's the probability of x equaling to n given y equal to y times f sub y of y by our fact. Here it should be y, it should be lambda. D lambda. Okay. Now that's equal to, okay, so here this conditional probability, you might remember, we talked about sometimes computing conditional probabilities is easy by putting ourselves in the given situation. So we're saying that the lambda, oh, this should be lambda. We're saying that the y is equal to lambda here, okay? And with that being the case, and you say, what's the probability x is equal to n? So we have an integral from 0 to infinity. Well, x was Poisson distributed, so that's e to the minus, and we need to have its mean. Well, that's going to be lambda, n. Okay? And so then it would be lambda to the n, all over n factorial. And then here, this is gamma distributed, with having lambda times e to the minus lambda, PDF, and d lambda. And so that's equal to 0 to infinity. I can pull out the 1 over n. And this is e to the minus lambda n, lambda to the n plus 1. Okay? And here, really, this should be e to the lambda n plus 1. Let me write that a little better. Okay, that's what we're looking at. D lambda. I made a mistake. I'm very sorry. It's not e to the minus lambda n, it's just e to the minus lambda, the Poisson distributes. E to the minus lambda, lambda to the n over n factorial. I made a mistake. I got confused in partial, in part with the gamma distribution. It should be e to the minus lambda. So what I've written here is incorrect. Let's make that correction. Okay, so here, this is e to the minus 2 lambda. I'm sorry. Then this would be lambda to the n plus 1, and then d lambda. Okay, that's what I got. That's correct. Okay. Now we've got to compute this integral. Okay. This wasn't 1 over n. It's 1 over n factorial. There's another typo. This wasn't a typo. That's just a mistake. All right, now, here's what we do. To compute this integral, note the following. Or I should say, now consider a gamma distributed random variable lambda. I'm going to call it capital lambda like this. Okay? With parameters what am I doing? I'm trying to put myself in a position where I can compute just this integral, okay? With parameters alpha equal to n plus 2, and I'll say lambda sub 1 equal to 2. Then the PDF of this big lambda is f sub big lambda estimated on little lambda, and it's equal to, okay, so this is for gamma. So we write down lambda sub 1, so it's 2 times e minus lambda sub 1. Okay. So that would be minus 2. Okay. And then I think times lambda, the input variable. So lambda sub 1 times the input variable. And then it's the input variable, which is lambda, times the parameter, which is 2, so it's 2 lambda, raised to the alpha minus 1, so that'd be n plus 1, all over gamma of alpha, which is n plus 2. Okay, that's what we'd have. That is correct. Now that can be simplified. That's equal to 2 to the n plus 2 minus, I'm sorry, not minus, but e to the minus 2 lambda, lambda to the n plus 1, all over, now what is gamma of n plus 2 where n is a natural number? That's just going to be, we did this as a homework assignment, that's n plus 1 less than what we're evaluating gamma at, factorial. That's what we have. And so that's the PDF. Now what I know is if I integrate that PDF, so 1 has got to be equal to the integral from 0 to infinity, because the lambda here is greater than 0, our input, greater than or equal to 0, 2 to the n plus 2, e to the minus 2 lambda, lambda to the n plus 1, all over n plus 1. If we integrate this with respect to lambda, that's what we get. But this, you can take out certain things that don't have lambda in them. We have 2 to the n plus 2, and this is factorial, n plus 1 factorial, integral from 0 to infinity of e to the minus 2 lambda, lambda to the n plus 1, d lambda. And so using that, we get for the integral, which is what I was trying to compute. We get for the integral, okay? So the integral from 0 to infinity, lambda to the n plus 1, write it that way, e to the minus 2 lambda, d lambda, will be equal to n plus 1 factorial over 2 to the n plus 2. Okay. So, our problem, which is the probability that x is equal to n, is going to be equal to 1 over n factorial, which is where we left off, integral from 0 to infinity of e to the minus 2 lambda, lambda to the n plus 1, d lambda, and that's equal to 1 over n factorial. We just discovered what that integral is equal to, times n plus 1 factorial over 2 to the n plus 2, which is equal to n plus 1 over 2 to the n plus 2. And that's the probability that we'll have a randomly selected policyholder will have a n number of accidents in that year. That's what we get. Okay, why don't I try to get in the next example. It's lengthy as well. We'll work on it. It's lengthy to write up, lengthy to find a solution to it, but it's okay. We get it done. Here's an example.
suppose that the number of people who visit a yoga studio each day is a Poisson random variable with mean lambda. Suppose further that each person who visits is independently female with probability P okay, or male with probability of course that's 1 minus P. Okay, I'm off the screen, I guess. So I'll write this over here with probability 1 minus P. Okay, find the joint probability that exactly n women visit the yoga studio, we're going to call it academy, visit the academy today. Okay. Very reasonable question. Let's start off with defining some random variables. So let's let n sub 1 equal to the number of women who show up, and let's say n sub 2 equal to the number of men. Okay, who visit the academy today. Again, this is a problem from our book, okay? Also let n be equal to n sub 1 plus n sub 2, and it's that random variable, n, that we're going to condition against to find the joint PMF. Okay, so n sub 1 plus n sub 2, we're going to let that be the total number of people who who visit the academy today. Okay. So conditioning on N. We have, okay, so here's what we're interested in. Joint PMF, that's probably n sub 1 equals to n, and n sub 2 equals to m. Okay, that's going to be equal to, it's going to be, by our fact, it's the sum as I runs from 0 to infinity of the probability that n sub 1 equals to m, and n sub 2 equals to m, given, gosh, I'm running out of room. Let's put it down here. Equals to the sum as I run from 0 to infinity. Probability that n sub 1 equals to n sub 2 equals to m, given that n is equal to I, the sum is equal to I, times the probability that n is equal to I. And then here, note that the probability that n sub 1 equals to n sub 2 equals to m, given that n equals to I, well, look, the chance of this happening is going to be 0 when I is different than, when I is not equal to m plus n. Okay? So the sum of these has to be equal to the big N. So this sum here really just has one term. It's non-zero. Okay. And so the probability that n sub 1 equals to n sub 2 equals to m, and it's going to be equal to, so this one term, what is that one term? That's going to be the probability that n sub 1 equals to n sub 2 equals to m, given that n equals to n plus m, times the probability that n equals to n plus m. Now, n, the number of people show up, that is, it was a Poisson distributed random variable. So this is equal to, this guy I'll leave alone. But this part, I can say what that equal to, because of it being a big N being a Poisson distributed random variable. It's e to the minus lambda. Lambda was the parameter, you might remember. Lambda to the n plus m all over n plus m factorial. Now, we're going to concentrate on this part. For this conditional probability, okay, we can think of where each person is solved. Who comes in is independently a woman with probability P, or a man with probability 1 minus P.
What we mean by independence here is that what happens for one person coming in doesn't affect the next person coming in. Doesn't affect the likelihood of the gender of the next person coming in. Okay. So probability P. Okay. We may think of this probability. This is a little p here. N sub 1 equal to n, n sub 2 equaling to m, given n sub n equaling to n plus m. We may think of it as a binomial random variable with n plus m trials, and think of the woman coming as a success, with the probability of a woman equal to the probability of success, and in this case, that's equal to P. That's what we can think of. P. All right, so, original question, the probability of n sub 1 equals to n, and the probability and n sub 2 equals to m, which we now know to be this probability of n sub 1 equaling n sub 2 equaling m, given n is equal to n plus m times, times the e to the minus lambda, lambda to the n plus m, all over n plus m factorial. What we're going to work with is this probability here, thinking of it as a binomial random variable. That's going to be equal to n plus m, choose n, times the probability of a woman raised to n, times 1 minus the probability, 1 raised to an m, and then times e to the minus lambda, lambda to the n plus m, all over n plus m factorial. Simplifying this will be n plus m factorial over m factorial times n factorial times here, let's write this as p to the n, and here I'll take one of those lambdas. This is lambda to the n times lambda to the m, so I'll take a p here that's raised to n, and a lambda that's raised to an n, and I'll rewrite that as p times lambda raised to n. Likewise, I'll have 1 minus p times lambda, all that raised to the m. Here's e to the minus lambda, and then this is all over n plus m factorial. This n plus m factorial, that n plus m factorial will cancel. We're left with 1 over n factorial on the bottom. Probability of lambda raised to the n. And what I'm going to do is I'm going to rewrite this e sub lambda. It's e to the minus lambda times p. Okay, that's that part. And then I'm going to have the 1 minus p times lambda raised to the m. And then here I'm going to have e to the minus lambda times 1 minus p. And if you check out these quantities for either, this is e to the minus lambda, which is what we want. This is e to the lambda p, and when you multiply by e to the minus lambda p, you get 0 there. You get 1, e to the 0, which is 1. And so those are the same. All right, so that's the joint PDF, and that's the answer to the question. To the question. But there's more that I want to say about this. Okay, there's some more observation that we can generalize from this problem. But we will wait for that till our next video lecture. Thank you very much for your time and patience.